Okay, I hope that's clear. Thank you very much for coming to this this presentation today from wherever you are. I am down here in Melbourne, and I'm very honoured to have the opportunity to speak to you today. Melbourne is experiencing a lockdown at the moment. So this is the view of the university, which I have not seen for since March. The University of Melbourne, where I work, is located on the edge of the Melbourne Business District, Central Business District. A very pleasant campus, and the University of Melbourne is one of Australia's leading universities. And the pleasant city of Melbourne has a very strong tertiary education tradition, as well as a strong coffee culture. And I invite you to visit us, and I can share with you one of my favourite cafes shown by these yellow dots. But it's a great pleasure to be speaking at the Joseph Stephan Institute. And thank you, Simon, my PhD student who's presently at the University of Vienna, who kindly took this photo of Joseph Stephan's monument at the university to show here in this talk. I'm particularly enthusiastic about Joseph Stephan's work, because for a number of years I've been going around the country giving lectures on physics, power and climate change. And I can assure you the Stefan-Boltzmann formula is the most important bit of physics I want to convey in those public lectures. So it is a really great honour to have the opportunity to speak to you through the Institute today. So here's the outline of my talk. I want to spend the first part of my talk with a quick retrospective to look at the dawn of the computer age and how that feeds into where we are right now. And then in the middle part of my talk, I want to describe the promise of quantum technology and the quantum atom's useful spin, which we're hoping to engineer, and we have engineered. And then finally, I'll conclude with some details of our work in building a large-scale quantum computer device in silicon. So first, a quick retrospective. I want to talk about the seeds of a revolution and the dawn of the computer age. So I had occasion recently to reflect back on 1958, so that's roughly where I'll start with this retrospective. That was also when the first US satellite went into orbit, the Explorer satellite, that was equipped with a Geiger counter, and it discovered the Van Allen radiation belts, beams of 100 MeV protons that pass through the Geiger counters on the machine, and means that if you go into space, you must make sure your electronics is radiation hard. And then if we fast forward to 1969, we've just celebrated the 50th anniversary of the Apollo 11 landing. And this was a remarkable event. It was not the dawn of the space age, as it's often badged. It was, in fact, the dawn of the computer age, because for the first time, a vehicle that was too complex to be controlled by human agency was equipped with a cutting-edge silicon device, a computer, 2,800 silicon chips, 6 transistors per chip, and a massive 70 kilobytes of core memory to control the whole machine. So this was I think this is probably the first time a computer was in control of such a complicated machine, and set the precedent for what was to follow. Then if we fast forward to the present day, we find the Mars Curiosity rover cruising around on the surface of Mars. Mars has a very thin atmosphere, and so GeV protons from the cosmic rays are constantly bombarding the machine. And sure enough, when you look at the signals from the computer motherboard, you see frequent big spikes due to the electron hole pairs induced in the silicon chips as a result of the passage of these high energy protons. This chart here is a record while it was in flight between Earth and Mars. However, after it landed, these spikes did not stop because the Martian atmosphere is too thin. But what remarkable progress in 50 years from the Apollo missions. This is a 200 megahertz motherboard, specially made in the United Kingdom, radiation hard, 256 megabytes of CPU memory and 2 gigabytes of flash. A much more sophisticated machine, staggering progress. Then in 1958 was the first flight of the Boeing 707, which was revolutionary for Australia because it opened up the world for travel in the days when we were allowed to travel on aeroplanes. And if we fast forwarded to today, of course, we now have supersonic transports that can take us anywhere on the planet in just a few hours. Well, actually, no, that's not true. That didn't happen. Instead, what we got is that. Okay, so not all progress is linear in the right direction. But in 1958, if you wanted to make a phone call, you used this for the benefit of the young people in the audience. That's a telephone, in case you don't recognize it. It only had a single app. That was for making telephone calls. You couldn't update it or install new apps. But if you fast forward today, of course, we have something much more powerful, our mobile phone. In 1958, if you wanted to take a photograph, you used an SLR camera. This was the SR7, one of the first domestic SLR cameras available for the mass market, and it used silver halide technology, the most beautiful quantum nanotechnology you've probably never heard of, but now unfortunately obsolete. Needless to say, fast forward 50 years, this is what we would use instead. Likewise, in 1958, if you wanted to do a calculation, you'd use a slide rule. And if you fast forward to 1958, yes, to the present day, you guessed it, you would use your mobile, again, the calculator app. Also, 1958, Jack Kilby developed the first integrated circuit, and the mission of the Nobel Prize Committee is to award prizes to those who during the preceding year shall have conferred the greatest benefit on humankind, they mean. So it's quite remarkable that it took them nearly just over 40 years to recognize the truly revolutionary nature of this invention of the integrated circuit. And of course, fast forwarding to today, you can buy an Intel CPU chip. This is an i7 with 6 cores, 14 nanometer technology, 5.6 billion transistors integrated into a few square centimeters of silicon, a truly astonishing technological advance from 1958. And what's important to note here is the cost per transistor in this device is about 10 nanodollars per transistor. And I don't think a human artifact has ever been manufactured at such an enormously low price. And for the benefit of those of you in Europe, that's about 3 nano euros per transistor. This technology, we have to keep in mind, has laid the foundations for where my talk is going tonight. Now, all this led up to the first quantum revolution. Microelectronics, optical fibers, global positioning systems, supercomputers, mobile phones, magnetic resonance imaging, and of course the modern tradition of being in a cafe and communicating with your family and friends and checking the news and not talking to the person sitting next to you. This is the first quantum revolution, has delivered this enormous change in our lifestyles. But I want to go back to a statement made by Paul Dirac in 1928, because the first quantum revolution has got some significant gaps. In 1928, Dirac said, the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known. And the difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble. And indeed, this is a limitation of classical approaches to computation. To overcome this problem, we're going to need a quantum advantage over the classical computers that we have today. So let me revisit the past, and between 1903 and 1913, remarkable advances occurred in our understanding of the fundamentals of the atom. And in fact, after Marie Curie discovered that the atom was actually a very complicated object and discovered radioactivity and radioactive isotopes, Ernest Rutherford reverse engineered the atom, or rather his students did under his supervision, and discovered the nucleus. And then just a few years after that, his postdoc, Niels Bohr, discovered the quantum atom and published his remarkable trilogy on the quantum internal machineries of electrons orbiting a nucleus. And it's worth noting that the first time Bohr's paper was presented at an international conference was at the University of Melbourne, my own university, in my own department, in 1914. That's because the British Association for the Advancement of Science was meeting in Melbourne that year, and Rutherford was the president of the association. Bohr was not able to attend the meeting, so Rutherford read Bohr's paper at the conference, and that was the first time, I believe, it was presented in a public forum. And we have detailed records of the questions asked of Rutherford after the presentation of Bohr's model for the atom. And it's interesting to see the chemists in the audience thought that the physicists should stick to physics and not intrude into chemistry, but there does seem to be a grain of truth in what he's described. Then in 1905, we have the revolution, and what Einstein did in 1905, his miraculous year in the annals of physics, was introduce what he later described, and has also been described by others, as his most revolutionary idea in a constellation of other revolutionary ideas. But he considered that his idea of the light quantum was his most revolutionary idea. The idea that when light is spreading from a point like a wave, it actually is absorbed as a particle. This perhaps is the first statement of the wave-particle duality. And now we know in the 21st century, since de Broglie, that matter does exactly the same thing. So this is the quantum advantage which we are going to seek to harness, and this is why I've made the title of my presentation, Einstein's Revolution. Then in 1959, Richard Feynman gave this remarkable talk, there's plenty of room at the bottom, about the virtues of nanotechnology, as we would call it now. And he included this throwaway line in his talk: we can use not just circuits, but some system involving the quantized energy levels or the interactions of quantized spins. So here for the first time is the idea of using quantum mechanics to do computation. And not much happened for a very long time. 1995, Seth Lloyd had this article in Scientific American suggesting using rare earth salts for storing quantum information and doing computations. And he introduced the term here, quantum mechanical computers. But again, nothing much happened. The technology just wasn't available to make these visions a reality. And in 1998, Bruce Kane, then a postdoc at the University of New South Wales, our colleagues in Sydney, published this remarkable single author paper, A Silicon-Based Nuclear Spin Quantum Computer. And this paper really triggered a phase transition in our interest in the potential of quantum computing. And today this paper, as I checked just before I started my talk here, has had over 2,900 citations, a truly remarkable revolution. So today, Bruce Kane's idea has evolved into this schematic of a flip-flop qubit involving two phosphorus atoms separated about 200 nanometers and individually controlled with gate electrodes to entangle them and put them in superimposed states as the fundamental element in a large-scale quantum computer. So that's my introduction. Now let me turn to the promise of quantum technology, the quantum atom and its useful spin. So the basic idea of the quantum capability we seek to harness is the idea of quantum parallelism. First of all, let me just remind you what a classical bit is. This is an abacus, an ancient classical computer, but the principles of the abacus are still used in your Pentium chip today. So just to remind you, on an abacus, you have a bead, which can be down, representing a 0, or it can be up, representing a 1. Now, imagine you took the wire on which that bead moves, pulled the wire out of the frame, and allowed the wire to occupy any orientation in space. This is indeed a quantum bit with its orientation given by a coordinate on what we now call the Bloch sphere. So instead of just encoding a 0 or a 1, this quantum bit with its wire that can occupy any orientation in space on the Bloch sphere can now encode an enormous amount of information depending on how it's programmed and oriented in space. Now, the interesting thing about this quantum bit, which is a superposition of the old classical 1 plus 0, is that when you measure it, it decoheres to either 0 or 1. You never measure directly the superposition where it's pointing away from the classical values of 0 or 1 on the Bloch sphere. But as long as you don't do the measurement, you can use this enormous information coding capability of the Bloch sphere to do very large-scale, massively parallel computations to simplify the idea. And today, around the world, there is a second quantum revolution underway. I've just culled from various journal articles and websites that most countries in the world have now got a major program to develop parts of this second quantum revolution, including right here in Slovenia with its Centre for Quantum Technology. Our centre down in Australia is a consortium of universities mostly located along the east coast, where we have multiple programs looking at different aspects of the second quantum revolution, all the way from single qubit applications for sensing in biology, through photonic qubits, through our ambitions of creating a large-scale device based on spins in silicon. My group is in a tight superposition with our colleagues at the University of New South Wales, and so we have a production line for our quantum devices that starts the fabrication at the University of New South Wales. They're then shipped 800 kilometres down the road to us in Melbourne, where we insert one phosphorus atom, and then they're shipped 800 kilometres back to the University of New South Wales for completing the fabrication steps and measurement. So let me just touch on some of the quantum attributes that we seek to harness in this second quantum revolution. I've mentioned the idea of superposition, of encoding information as a qubit with its orientation on the Bloch sphere. If you like, this is quantum parallelism. But we also have these other intriguing quantum attributes that have no classical analog. Entanglement, Einstein's spooky action at a distance, where qubits, photons, produced as a result of a cascade in an atom, retain common attributes such as, or complementary attributes such as polarization, even though they're in indeterminate states and only collapse to the classical polarization of, say, vertical or horizontal upon measurement, regardless of how far apart they are. No hidden variables govern this behavior. They truly are in an indeterminate state during their journeys. Of course, quantum tunneling is responsible for the nuclear reactions, or promoting the nuclear reactions that occur on the sun. Thermonuclear fusion is fundamentally a quantum mechanical process, and Esaki diodes harness the same quantum tunneling phenomenon for electrons in semiconductors. Coherence is a quantum phenomenon where the quantum state of being superimposed in two places at the same time on the Bloch sphere exists in a whole lot of different architectures, including phosphorus in silicon, which is the main focus of my talk, but also color centers in diamond, electrons in quantum dots, photons, as I've mentioned, and a whole lot of other quantum particles which could be harnessed for different quantum technologies. And of course, the flip side of coherence is decoherence. Coherence is exquisitely sensitive to being perturbed by the environment and causing the quantum states to decay or collapse into their classical equivalence. And so the phenomenon of decoherence, the collapse of the wave function, is exquisitely sensitive to environmental perturbations, and hence the idea of using decoherence as an environmental sensor. And of course, the teleportation of quantum states is possible over very long distance, where superpositions are encoded in photons and can be transmitted over very long distances, possibly for a quantum internet. So here's how one would exploit these quantum attributes for new devices. Quantum computing is the flagship application. Here is a caffeine molecule, one of the most important molecules for physics. It's got 100 electrons in the outer shells of all the atoms that go to make up this molecule. But even the best supercomputers today would be struggling to model more than 30 electrons in a complicated molecule to find the structure. But a quantum computer could easily, with sufficient qubits, could indeed solve for the structure of the caffeine molecule. But for now, you have to get out the test tubes. You can't do this using the laws of physics. It's just too complicated, as Dirac already indicated. Quantum sensing has now become an important field of investigation and applied technology, using particularly color centers in nanodiamond to sense magnetic fields at the atomic or at least subcellular level in important biological systems. And perhaps entangled photons could also be used for new sorts of radar, particularly for distinguishing friends and foes. Quantum cryptography is already commercially available for secure key distribution, where communication security is guaranteed by the laws of physics rather than human ingenuity. And as I mentioned already, a large-scale quantum internet could be a feature of the mid-21st century to develop distributed computational power that greatly exceeds what's possible with the classical internet. Now, there's a large number of rival qubit systems being investigated around the world right now. Ion traps have particularly attractive quantum attributes, and they exist in a vacuum, which is the almost the ideal medium for doing quantum mechanics. And these machines have reached a very advanced stage of development with multi-qubit machines already in operation. There is also a magnetic flux qubit based on counter-rotating superimposed, that is, currents of electrons in superconducting flux loops, where the magnetic field is therefore polarized in the either up or the down directions, or in a superposition. And D-Wave has commercialized this technology to make what they call an adiabatic quantum computer. Transmons, or transmission line shunted plasma oscillations, sometimes called charge qubits, have also reached quite an advanced stage of development, and tens or maybe even 100 qubits based on this technology are now being pursued by several organizations. The nitrogen vacancy center itself in diamond also offers the promise of robust quantum computing in a large-scale device, albeit with formidable engineering challenges. And of course, donor electrons on nuclear spins in silicon is the technology of choice for our center. There are two different flavors of the silicon device. There's the one based on donors, as I mentioned, but there's another architecture that uses very similar nanocircuitry and control sequences where there is no donor, and the electron instead is suspended in a quantum well configured by nanoscale electronic gates to hold just one electron and allow it to interact with adjacent electrons. The big players are very far down the track already. IBM has just released yesterday its roadmap for the development of quantum computer technology. They now offer internet access to their 65 qubit transmon machine and have an ambitious and aggressive goal of having a 1,000 qubit machine in just a couple of years. That was a roadmap that just came out yesterday. I mentioned the D-Wave machine with 2,000 adiabatic magnetic flux qubit, not really a general purpose programmable machine, but is very optimized for certain classes of problems. Rigetti is offering already quantum cloud services and quantum algorithms. Microsoft is looking at topological non-abelian anyon quasi-particles in their device, Majorana fermions, etc. I'm still working on understanding exactly what that is. And Google is also looking at flux qubits and transmon architectures with a very aggressive roadmap aiming for millions of qubits in the future. And Intel has just recently announced the availability of its 49 qubit processor. I've been to some talks by personnel from the Intel labs, but I'm none the wiser into exactly what technology they're using for this 49 qubit processor. If you have a look at the press release on the Intel website, you just see a board with a whole lot of SMA connectors on it, which doesn't say what the technology is. Of these big players, my colleague Lloyd Hollenberg is a member of the IBM Q partner organization, where he runs a big program in developing quantum algorithms that can be run on the IBM transmon machine over the internet to run quantum algorithms on a real quantum computer. It's a remarkable advance on just a couple of years ago. And in reflecting on the Jan Meyer's talk on day one of our conference on Monday, I should say a few more words about Diamond, because Diamond has this remarkable nitrogen vacancy color center, which is a qubit at room temperature and can be optically programmed and read out. A really remarkable and possibly unique qubit. I don't know that there are any other optical qubits in Diamond or any other material that are as versatile as the NV center, although other people are looking for alternatives because of the engineering challenges. And this nitrogen vacancy color center has been employed in a whole lot of remarkable experiments, all the way from fundamental physics, where this remarkable paper looked at the emergence of classicality from the quantum superposition using a nitrogen vacancy color center to probe the quantum state of adjacent carbon-13 isotopes in naturally occurring diamond. There's the proposal for this quantum simulator from our colleague Andy Greentree at the Royal Melbourne Institute of Technology. Quantum communication networks are already being rolled out based on nitrogen vacancy color centers. Nitrogen vacancy color centers are used for mapping electric currents at the nanoscale, is also a subject of active research, as well as the nanomagnetometry that I mentioned already. And Jan's talk on Monday mentioned the idea of building a large-scale quantum computer employing diamond nitrogen vacancy centers that are coupled to arrays of carbon-13s. The carbon-13 isotope has a spin half nucleus, and so can act like a quantum memory. A very interesting architecture, and it's look forward to seeing a large-scale qubit machine operating at room temperature in the near future based on this technology. But for now, I want to return to the quantum atom and its useful spin, and say a few words about the work we're doing. So first of all, I should put up some pictures of my laboratory. We had a very nice virtual tour of the laboratory there in Slovenia yesterday. So we also have an accelerator. Ours is vertical, and there's a 90-degree magnet in the basement, and we have a number of beam lines. The green line here is a nuclear microprobe that is used in the quantum computer project to investigate some of the chips we're using in the project. It plays a very essential role because we developed a lot of expertise with ion beam induced charge using this machine, which is a method we've adapted into the KeV ion regime, as I'll describe. But adjacent to our accelerator lab, we also have an extensive cleanroom complex for doing electron beam lithography, optical lithography, and we also have a low temperature measurement system with a 10 millikelvin refrigerator and a 9 Tesla superconducting magnet. And then just further down the hall, we have our single ion implanter, which I'll return to in the last part of my talk. And just recently, we've developed an electrically detected magnetic resonance system where we can implant devices with our KeV implanter and then bring them into this lab, cool them down, and put electric currents through them to measure the spin state of the implanted donors. This has been a very major development overseen by our postdocs, Brett Johnson and Daniel Creedon, and Danny Holmes working on it for her PhD thesis. So here's where I am right now, as you can see from my background, deep inside a silicon crystal lattice. And by replacing one of the silicon atoms with a phosphorus atom, we have a qubit. The phosphorus atom has a spin half nucleus. It can be up and down, or up or down, or up and down in a superposition, and orbiting the phosphorus atom is the donor electron. But in natural silicon, we have about 4.7% silicon-29, a rare isotope, but it has a spin half nucleus, unlike silicon-28, which is the common isotope. And that spin half nucleus is like a little bar magnet flipping around uncontrollably that couples to our phosphorus qubit. So we don't use natural silicon in our experiments. We remove the silicon-29 and replace it with silicon-28. And this enriched silicon-28 is like a semiconductor vacuum. There are no unpaired spins except for the phosphorus donor that we've engineered. It's called the semiconductor vacuum, the next best thing to a real vacuum for doing quantum mechanics. Then we can, by means of radio frequency pulses, flip the spins of our two qubits, the nuclear qubit with radio frequency pulses, or the electron qubit with gigahertz microwave pulses. And of course, by keeping the fields on, we can put these qubits into the superimposed state and rotate them around the Bloch sphere. So this is how whoops. Sorry. This is how the device, the architecture of our device works. We want to be able to control and read out the orientation of a single nuclear or electron spin from a phosphorus atom, shown here in this cartoon. Imagine we are now inside a block of silicon looking up towards the surface, we see a single phosphorus donor that's been inserted in my lab, and on the surface of the silicon there are these electrodes. And by means of programming voltages on these gates, we can bring an electron from this single electron transistor onto the phosphorus donor, and then with the radio frequency pulses we can control it, and then by pulsing the gate we can bring the electron back onto this single electron transistor and read out its spin orientation. So this architecture allows single atom qubit gate control, programming with the radio frequency pulses, reading it out with the single electron transistor. And this is what the device looks like in reality. This is 10 million times actual size on your screen. You can see the surface circuitry. We remove the silicon 29s by using enriched silicon 28. We implant a whole lot of phosphorus atoms into this small area in the middle, and then by programming the gates on the surface, we're able to zero in on just one of the implanted phosphorus donors. So the number of phosphorus donors in this device are subject to Poisson statistics, and we post-implant select a donor of interest. And then we can do the programming and readout, and we find that the lifetimes of the electron qubit in silicon 28 at 100 millikelvin is 1/4 of a second, and the nucleus in an ionized donor sits serene and isolated from the outside world and can live for 30 seconds or more. Truly remarkable, very robust, long-lived qubits. By the way, for the benefit of you who are not so familiar with the quantum technology field, this is how we achieve a superposition. You can imagine this is an electron qubit, and here's the microwave pulse, which flips the spin from the spin up state to the spin down state. Then, as Einstein taught us, if the microwave field is still on, you'll induce a decay, stimulated emission from the spin down state back to the spin up state. So while the microwave field is on, the qubit is in a superimposed state. Then you turn the field off, and this is for my undergraduate lectures. The electron is spin up and down. But then when you measure it, you might expect to see it down or up. And if you asked a classical physicist, say Galileo or Newton, they'd say, well, surely, depending on when you turned the microwave field off, you'd either get it up or down, and you just get a 50% chance of reading it up or 50% chance of reading it down, depending on what state it happened to be when you did your measurement. But indeed, you don't see this. When you do this in reality, you find that as a function of time after you turn off the microwave pulse, the qubit oscillates between up and down. And these are the Rabi oscillations, a characteristic of a quantum state that go on for a very long time. And of course, you have to have an observer to decohere it. So here's myself and my colleagues at the University of New South Wales observing the decoherence of our electron qubit. It was a wonderful result. And we've now investigated very carefully all the different sources of decoherence in our device. Remarkably, the control gates, the residual silicon 29s, the nearby phosphorus atoms, and phonons and strain can all be distinguished and untangled. And despite all these sources of decoherence, we still have very robust qubits, and some of the most robust qubits that it's possible to have in nature. And I should mention we've removed the silicon 29. So our accomplishments to date, a whole lot of single donor spin physics, the revelation of the long-lived single nucleus spin coherence. Of course, that's been known since the 50s. A Bell's inequality measurement. We've succeeded in building coupled donor devices just using Poisson statistics. But the most important thing I want to conclude with is our new developments in deterministic ion implantation, where we move beyond Poisson statistics into counted atom devices. So just to conclude now, our work building a large-scale device by implanting phosphorus qubits in silicon-28, where we have arrays of donors 200 nanometers apart that are coupled by inducing electric dipole moments by polarizing the donor electron, which allows qubit-qubit coupling over long distances. So this is how we plan to put the donors into our device. We have a nano stencil fabricated in an atomic force microscope. By putting an ion beam on our nano stencil, ions can pass through a tiny aperture and then implant with the required precision into our devices. Here's one of the chips designed by Melvin Jacob, my postdoc, who mounted on a charge-sensitive electronics preamplifier of advanced design that allow us to record the signals from single ion impacts that arrive at random time intervals and then advance the cantilever to the next implant site step by step. And Simon Robson, who you met at the beginning of the talk, has fabricated very tiny stencils into the atomic force microscope cantilever for collimating the beam to the required precision. So this is state-of-the-art counted atoms. Here's one of our chips with an array of construction sites, each with the chip wire bonded to the charge-sensitive electronics. Here's the atomic force microscope image of the substrate. And then we implanted, in this case, just at random locations through a large aperture to test the system. Here's the pulse height spectrum that we get from this device. And here are the arrival times, random stochastic arrival times of 200 donors into the construction site. In previous conferences, I played this soundtrack so you can hear the donors arriving. But let us move on. Just very recently, we succeeded in also using ion implantation, not only to implant the qubits, but to pre-enrich localized areas on our chips using a high-fluence silicon-28 implant. It's always been a bit of a bottleneck to source enriched silicon. So we use a high-fluence silicon-28 beam to selectively enrich areas for the construction of our quantum computer device. And just in the last month, we succeeded in doing electron spin resonance on phosphorus atoms implanted into this enriched material. And we see a very satisfactory T2 time for the electron spin on these implanted donors. Not a trivial experiment, but it means it now opens the way to producing very significantly depleted silicon-28, depleted in silicon-29, where we anticipate very long coherence times. This is a new technique. We're just about to send off a paper this week. And you can see the depletion of the surface layer we've achieved down to 250 parts per million of residual silicon-29, better than the commercial suppliers, and we believe we might even one day be able to approach the purity of Avogadro silicon. So by that ESR measurement revealed that all the problematic decoherence mechanisms had been cleaned up in our device. So now we have all the tools we need to build a large-scale device. We have an architecture with relatively relaxed fabrication tolerances that we can achieve with our atomic force microscope nanostencil. We have a method of coupling all these qubits together with control circuitry on the surface. So this is going to be our task over the next 5 years, to build a prototype device, perhaps with 5 or maybe even 10 qubits using this technology. So what's the end of this first part of the second quantum revolution? We know already that in biology, quantum mechanics is harnessed for things like photosynthesis, for transporting quantums of excitation from the absorption of sunlight through many paths to the conversion site where the absorbed solar energy is used. We know that some birds appear to use quantum entanglement for magnetic sensing. And of course, DNA mutation by proton tunneling has been around for a long time. But what I am really enthusiastic about is in the future addressing Dirac's challenge of applying the laws of physics that we understand so well to what have previously been intractable problems in chemistry and biology. So imagine you were trying to model a penicillin molecule, an antibiotic, 41 atoms, but so many electrons, you'd need 10 to the 86 qubits, 10 to the 86 classical bits to model all the possible electron-electron interactions in this molecule. But with a quantum computer, you might only need 200 qubits to model this molecule. So this leads us then to where we are with this. In 2020, IBM reported modeling a 2-atom molecule. Okay, 2, it's the first step, using their 16-qubit machine. And just this morning in my news feed, I see an article in Physics Today where Google reports using their 54-qubit Sycamore chip, modeling a chemical reaction using Hartree-Fock methods, but using quantum mechanics to do that. So where are we? We have just entered, according to John Preskill, the quantum computing in the noisy intermediate scale quantum technology era, where we have the equivalent of the Apollo computer, perhaps, where big companies are now churning out machines at the 50-qubit level and algorithms are being developed. Single qubit sensors and what have you have already been marketed now, and single photon sources for quantum communications. But in the near future, once we move beyond the noisy intermediate scale quantum technology era, we might see the development of killer apps on these early machines that incorporate error correction codes. A robust qubit really needs perhaps 5 or 10 physical qubits to guard against errors and run error correction algorithms. We may have 100 qubits or even 1,000 in the next couple of years, but there's still an engineering chasm to the goal of a machine that could do useful tasks such as design antibiotics. You need 1 million qubits or perhaps 1 billion qubits if you're going to incorporate error correction mechanisms. But even today, we're starting to see articles about drug discovery with quantum computers. And maybe one day it'll be possible to reverse engineer killer viruses and then design drugs that will counteract the terrible toll of life and limb that COVID-19 is taking around the world right now. And I'm really sorry if you've been personally affected by this very nasty virus, but hopefully we can bring physics to solve this problem using an advanced, large-scale, billion-qubit quantum computer based on what we already know how to do with classical CMOS in the very near future. And we can bridge this engineering chasm. Thank you very much for your attention.
Thank you, David, very much. So I'd like to thank you on behalf of everybody in the audience. Now there's time for questions. So what I suggest is that everybody, whoever wants to ask a question, raise hand, and then you can go ahead with that. So now you're welcome to raise hands and unmute yourself and then ask questions. So while the audience is thinking about it, let me ask you, so you said that your plan is to develop a 200 qubit device?
Over the life of our center for quantum computation and communication technology, we hope to get to 5 or 10 qubits. It would be difficult to go to 100 in a university laboratory because of the control circuitry that you need. There was an image, or a photograph on my newsfeed this morning of an IBM engineer working inside a gigantic dilution fridge that was like 2 meters in diameter, designed to be cooled to a few hundred millikelvin or below for a 100 qubit machine. And I don't think too many universities would have the resources to build such a gigantic machine. I should say, though, that's a consequence of the transmon technology, which is very, the qubits are very bulky. One of the advantages of our approach of using single donors is that the qubits are very compact. And so possibly we won't need dilution fridges that are 2 meters in diameter, but we can make something more compact, something more equivalent to a Pentium chip, but containing not billions of classical transistors, but billions of quantum bits with the necessary CMOS control circuitry, or the equivalent control circuitry for the millikelvin operating regime.
So I imagine that the commercial manufacturers or developers of these machines and devices they know about your technology very well. So have you been approached by them, or do you talk to them?
Yes, we do talk to them, but representatives from the big players are now increasingly attending the conferences that we organise. But it's remarkable that the big players have chosen to recruit whole research groups out of universities and bring them inside the fence to develop the technology in a secure environment. So that hasn't happened to us yet. I have to say that if we had a 50 qubit device based on donors in silicon, it might be a little different. But so far, we've only just recently been able to publish results on 2 qubit devices. But I'm hoping once we get our deterministic devices constructed and measured, there might be interest from the big players. But I noticed that Intel just recently put out a patent where they showed the architecture of a device that included a single implanted donor qubit, but the patent was silent on the technique they were using to just put 1 qubit in each cell of their device. So I know that Intel is very interested in donors in silicon, as you'd expect.
Yes.
So can I ask one question?
Sure, go ahead.
So as the number of qubits will increase eventually in the future, what are the, let's say, solution for that technological aspect, like engineering? How to basically read out or manipulate information to these qubits? Are there any idea? I believe this is quite a big challenging issue in the future.
Yes.
Yeah. So what are your thoughts about that? How will you be able to solve it, or I mean the ideas to solve it?
Well, you ask a very relevant question, because the architecture for harnessing the qubit is just as important as the quantum attributes of the qubit itself. Exactly. So a number of large-scale architectures have been published for donors in silicon. My colleague Lloyd Hollenberg has developed some of these, and my colleague Andrea Morello for the flip-flop qubit has also published a similar large-scale architecture. Basically, the idea is to either couple whole arrays of donors to single electron transistors, or to couple the donor to a microwave bus, where the quantum state of the donor controls the microwave photons in the bus, and then can be transmitted from place to place on the chip. But yeah, I mean, I wouldn't, although I know how a transistor works, and my postdocs have even made FETs in my lab, I really couldn't tell you how a Pentium is able to cram billions of transistors into a few square centimeters of silicon. So that will definitely need the expertise of CMOS device engineers to perfect the architecture for these devices.
Thank you.
But it's been solved for classical machines.
But
So
it hasn't been tested so far. I mean, for Qubit, this architecture hasn't been tested so far. It is just a design.
Just a design.
Okay.
But we have done 2 qubit devices, but using only Poisson statistics. The deterministic devices will come in the next year or so.
Okay. Thank you.
Are there any other questions? You're welcome to raise hand or just turn on your mic and then just ask.
Tomasz Mertel here.
Yeah.
I have a kind of related question. So during the talk, it was mentioned that you basically manipulate your qubit by a microwave field. How do you address different donors if there are several on chip with microwave field?
Okay, so there are several techniques where you can Stark shift the resonance, Stark shift the qubit into resonance with a background microwave field, or you can ionize the qubit by removing the electron from a donor atom. There's a whole variety of different methods. Our plan, it turns out that in the devices we've made to date, you can control each qubit independently because of the gate voltage needed to ionize the qubit. So qubits that happen to be very close to the island of our single electron transistor can be ionized with a relatively low gate voltage, but qubits which are much further away need a higher gate voltage. So in this way, we're able to individually select one donor atom for doing our experiments. So you could take that to a much larger scale, where you have bias voltages for programming your or selecting the qubit that you want to control. And in fact, one of the problems we have to overcome is that because of the inevitable straggling associated with the implant of an ion into silicon, each qubit will be different. This is not a problem faced with classical devices because each transistor within fairly narrow tolerances behaves in exactly the same way. So if we had a 1 million qubit device, we would probably have to use some kind of AI algorithm to calibrate the qubits first before the computer could begin to work. And such techniques are being developed and have been published already in anticipation of the need to do that.
Thank you.
More questions?
May I ask you some question?
Sure, go ahead.
Okay. Oh, very nice presentation. But I wonder what's the difference between the ordinary computer system to this quantum system in terms of software system. Software might be different from that computer. So the accumulated software cannot be used or modified, or completely new software must be developed.
Yes, that's a very good question. Our colleague, Professor Gerard Milburn from the University of Queensland, has written a number of books on the promise of quantum computing. And he says that quantum computers are not the next step from classical computers, but a whole new journey. So we do not expect that the software, the quantum software, will bear any resemblance to classical software. And indeed, the work that my colleague Lloyd Hollenberg is doing in training the next generation of software developers using the IBM machine has begun to develop the new techniques needed to run algorithms using qubits instead of classical bits. It's really quite a different approach.
So the software issue much more than the hardware issue, because a lot of software are already available in classic system. It spent more than 30 or 50 years spent. But in this case, the timing of software availability was shortened.
Yes, I'm not. I'm not sure how much skill in programming a classical computer will map across into the techniques needed for a quantum computer. There are a lot of concepts that don't exist in a classical machine, and this there's also a whole lot of things you don't have to worry about in a classical machine, like error correction and all that sort of stuff. So yeah, I think it really is a journey into a different direction for the quantum software compared to classical software. And in fact, I noticed that in the American Physical Society has published a number of articles on what's needed for a quantum future, and that those articles have identified that we have a great need for training the next generation of programmers with the skills necessary to run a quantum computer. So even though we don't really have a killer app available yet, people are already thinking about how that could be developed. And IBM, I think that's part of the reason why IBM has made their machines available on the internet, so people can experiment with programming them, and hopefully this will develop a very powerful application for these noisy intermediate scale quantum computers that are now becoming available. Particularly perhaps error correction techniques might be the first. Well, it has already received a lot of attention to guard against incoherence.
They should find some special applications and then shift to another applications, I think. Well, thank you very much.
Indeed.
There's another question by Dr. Reinert.
Hello, David.
Thilo, good to see you.
Yeah. Hi. The last question, I have a follow-up question concerning what you can do with quantum computing. You gave the outlook that we could fight the probably next or over next pandemic with calculating antibodies or therapeutics with quantum computing. But this is peaceful. What do you think are the implications, or what do you expect from using it in a more nasty way? When do we expect to have someone hacked into my bank account, for example?
I think, Thilo, that might have already happened using just classical techniques. But maybe the first killer app will be quantum key distribution for secure communication. I would prefer not to do all this work to deliver the promise of the second quantum revolution for purposes that were not for the benefit of humankind. So I'm inspired by the vision that we could overcome Dirac's objection or problem with physics not being able to be used for large-scale systems because they're too complicated, I would think it's a wonderful thing if we could overcome that problem, and problems that are presently intractable that we would like to solve could be solved with the second quantum revolution. And it's not just drug design. Our colleague Thomas Schenkel in Lawrence Berkeley Labs has convened a forum on quantum information for fusion. Fusion has been an extremely difficult problem that's humanity has been defeated, but we're still trying. But fundamentally, fusion is a quantum mechanical process involving barrier tunneling. So maybe there are new approaches to solving the problem of fusion using quantum mechanical techniques to understand it better. And there's some online resources if you're interested in following that up. I think that's a really visionary application. If we could figure out a way of achieving practical fusion using some quantum shortcuts to achieve more efficient barrier tunneling, that would be a wonderful thing. Probably on a par, on a similar level of quantum mechanical drug design, which is probably almost certainly going to need millions or indeed billions of qubits.
Thank you, David.
We have another question by Professor Garman.
Yes.
Okay, so...
Okay, so it's in the chat, right?
In the chat, yes.
Okay, so the question is there an issue technically that the temperatures of 100 millikelvin have to be so low for quantum computing? So, yeah, that's a very good question. And my answer, because I've been asked this many times, is right here. So this is my mobile phone. And this mobile phone gives the illusion that I can use it to search the internet to find the telephone number of the local restaurant to order takeaway food. But this phone does not do that. This phone does not search the internet. What this phone does is sends a request through the Wi-Fi to a computer in the United States or somewhere that searches the internet for me and then sends the information back to my mobile phone. So I would say that in the near future, I'll have a quantum computer app on this phone where I can, where necessary, perform quantum computations for some purpose, perhaps internet security, maybe not drug design, and it will tap into the quantum computer to do the calculation, and it'll give the illusion that I'm doing the computation right here on my phone. So, but it'll actually be using the machine in a cryogenic refrigerator somewhere in the United States or China or India or maybe even here in Australia to perform the quantum computing that I need to take advantage of its capability. So no, I don't see that the 100 millikelvin is a technical barrier. However, I mean, if the promise of diamond and the NV centers and the carbon-13 nuclear spin, if that can be realized, then maybe you could have a small quantum computer in your phone or in your laptop for special purposes, or indeed there may be commercially available single qubit diamond quantum devices for quantum key exchange over short ranges, but this could become a near-term quantum device, a 1 qubit quantum computer.
Thanks very much.
Thank you for the question, Elspeth.
So, so there's another question in the chat by Professor Cesare.
Okay, so the question is, for the same problem, what would be the speed up provided by a quantum computer with respect to a classical one? So this is the same answer from an earlier question, that the quantum computer is not just the speed up. of a classical machine. It's a whole different way of doing computations. So problems that you cannot do on a classical machine because the universe will not live long enough could be done using the massive parallelism implicit in a qubit. So people throw around all sorts of crazy numbers, millions, billions, trillions of times faster, but it's not really the point. The point is that we hopefully will be able to tackle problems that we don't even think about tackling because classical machines are simply never going to be powerful enough. Problems where the complexity grows exponentially every time you add another electron into the problem. So that to me is the key goal, to tackle things that we just cannot do now. Not just tackle things more quickly, but tackle things that are impossible with classical techniques.
We have another comment by Professor Reiter.
Yes, Istvan, thank you for your question. Another independent curve of Moore's law 2 should be fitted to the number of qubits. Yeah, quite right. At the moment, we've got just 2 data points, 2 qubits, maybe 6 qubits, and maybe a third one at 50 qubits. It's growing slowly, but maybe the doubling time is of the order of 12 months. But I suspect it won't. That won't continue. That as the number of qubits increase, it's not just going to be a matter of building ever bigger dilution fridges to hold the machine. There'll be a significant engineering chasm that we'll have to get across. So I don't think it'll go like Moore's law, but I could be wrong. Who would have thought that Moore's law would continue for 30 years?
Yes.
And I hope, the young people out there will think of things that the old guys never thought of and find ways of delivering on this enormous promise.
Okay, so there's another question by Professor Kada-sensei in the chat.
So this is the question about the noisy environment. It basically, is environmental radiation powerful enough to degrade the coherence time? Emphatically, yes. And that's why we have to isolate our silicon devices down at 10 or 100 millikelvin at the bottom of a dilution fridge to guard against the environmental radiation. Just infrared photons or even phonons in the silicon crystal lattice can decohere the qubits. For silicon qubits, of course, for diamond qubits, they are serene in the diamond lattice at room temperature. The diamond lattice is like silicon at millikelvin temperatures. So for a diamond device, room temperature environmental radiation is not powerful enough to decohere the device, which is why diamond is so attractive. And I think Jan has a question on this in this area. Is that right, Jan? You have your
Hello, David. Oh, I'm sorry I missed your talk. I will see it after that. I had a seminar, but it's right with the radiation. It's a very interesting question, and that is what we are working together with Milko. Milko, are you here? We worked on a program about this, how radiation, so nuclear, for example, alpha sources or something, could influence a quantum computer. And my question is, the superconducting stuff are really huge stuff, yeah. So they have, and that when you now calculate what is the size of this computer, then of course the chance that a cosmic event hits this computer is of course much higher as our example. In our case, we have only a few nanometers, so it's orders of magnitude lower the chance that it will be influenced. Do you make a calculation, or is it a wrong idea?
Well, as you know, cosmic radiation is a problem for classical computing, and as I mentioned, the CPU on the Mars missions has to be radiation hard. So they're classical computers that incorporate error correction circuitry, parity checking and all that sort of thing to guard against cosmic rays. And indeed, these days, your Pentium chip is made from carefully selected materials that have very low radioactive components, because the last thing you want is radioactive decay from a radium atom or some ubiquitous potassium or uranium naturally occurring right in the middle of your Pentium chip. And you're probably familiar with Jim Ziegler's first job at IBM was to figure out why so many of their VLSI word processors were being sent back to the factory from Denver because they kept crashing. And, you know, why Denver? And of course, Mile High City, they were very sensitive to cosmic rays, these early generation of VLSI memory chips, and they had to be re-engineered to make them less sensitive to upsets caused by cosmic rays. So that's going to be a problem for any large-scale device. You're going to have you have to protect not only the quantum bits, but also the classical circuitry that's being used to control it. However, here in the state of Victoria, which I must say is presently all locked down and nobody's allowed to go anywhere, but just when it opens up again, I'm looking forward to visiting a new laboratory we're building. My department is building, that's at the bottom of an old gold mine. This is a mine that is more than 1 kilometre deep. And at the bottom of this mine, they are putting a low background radiation laboratory, which will include dark matter detectors. That's the primary goal of this lab. But also there'll be a laboratory for putting cryogenic apparatus for doing ultra low radiation background experiments. And so I'm hoping that maybe in the future, we'll be able to get an operating machine perhaps developed and installed in this lab and connect where it will be well shielded from cosmic rays. But it is the primary problem with the quantum computer in silicon, at least, is not the cosmic rays. It's random electromagnetic background noise. However, I should mention that some donors, such as bismuth in silicon, when operated at a particular frequency, the first derivative of the energy of the transitions goes to zero as a function of the electric or magnetic fields. These are called clock transitions. And it's a quirk of the quantum state that at these particular operating points, the qubit is insensitive to random electromagnetic noise in the environment. And they're called clock transitions because they're particularly stable. So we are very interested in bismuth as an alternative qubit to phosphorus in silicon because it promises to be extremely robust against electromagnetic noise from the environment, and also suffers much less straggling than phosphorus in silicon.
Okay,
so
because our advantage is also that we can really build not only one quantum computer, but we can make a multi-core quantum computer.
Absolutely.
Yeah, and then of course, when one is not working, what helps? And we take it out and use what's up. When Google want to make a multi-core quantum computer, they need new buildings because every quantum computer is an own building. So they need a city to do this, and we can do it in one chip. And that's also a big advantage of our system compared to these people. Yeah.
Yes, although I have to say that the transmon qubits and the flux qubits are macroscopic compared to donors. So you know, these have a scale of microns, I believe. And therefore are much more robust against cosmic rays, at least. Not to electromagnetic interference. They still have to go into a fridge. But this is like running an old, you know, VLSI chip with such large transistors that the cosmic rays are not so troubling.
Okay. Yeah, thank you.
Thank you. So I see no other hands raised and nothing more in the chat. So I suggest we all thank, or I thank Professor Jamieson on behalf of everybody in the audience. This was really a fascinating lecture, and I think the discussion that followed, which lasted far more than I anticipated, also shows that the topic is really very hot and of broad interest. So
very cool, not very hot, very cool. 100 millikelvin.
Very cool. Yes, thank you very much. Thank you very much.
Well, thank you. Folks.
Thank you very much.
And I thank everybody for participating. And like I said, the video of this talk will be posted online in a few days, I guess.
Thank you.
All right. So thank you very much, and I'll see you next time.